So now we're going to talk about something that we call instantaneous velocity. What's the velocity at a given point in space? What we've talked about now is more discrete, and that means that I have to look at the change in position and then divide it by the change in time. But what if I want to know what the velocity is at an instant in time? And that's a little bit harder to do, and it requires some thinking. So what I've drawn here is some positions of a soccer ball being kicked by a soccer player at a set of different times. And you can see that this soccer ball travels in a parabolic shape, and we're going to talk about why it's a parabola later. But for demonstration purposes, I just want to point out that if I think about the vector quantity of the position of where the ball is at some later time relative to where it started, I'm going to start it here at point B, I have to draw vectors that connect point B to point C, D, E, and F, for example. And so what I'm going to do is I'm going to talk about the relative position vectors from here to here to here and to here. And so these vectors are defined by the values that we want to write down. And so those vector values are R from C to B. This one is defined as R from D to B. And this one's defined as R from E to B. And of course, this one is defined as R from F to B. Okay. And so those are going to be the relative position vectors that we can work out from this construction. Now, the velocity, the average velocity during these intervals would be, of course, this position vector here, or here, or here, divided by the amount of time that the ball traversed along this path. So the amount of time that's elapsed, and again, these are positions here. So this is the Y position, this is the X position. I kick my ball up in the air. I don't know the time that it takes yet, but I know there's some delta t's, and I'm going to say that each interval is separated by the same amount of time. It doesn't really matter so much. So to construct the average velocity, I need to take my, and I'll call these delta r's instead of just r's, my delta r, and that's from some point to B, over the delta t of that particular interval. Okay, well that's good, but that's going to really dramatically alter the actual value of the velocity, because these vectors are changing direction because of the nature of the directional change of the ball. And so what if I want to shrink the delta t to be the smallest possible interval that I can imagine? So that would mean that the position of the next point in space would creep towards B very, very closely. If I follow this arc, if I sort of blow up my arc and say, you know, this is point B here, this is B, and point C is way out here somewhere. As I bring points all the way back to B, you can imagine that my velocity vector will soon become a point that has to do with the very small, tiny vector that points from B to whatever point is very close by. However, delta t will shrink dramatically, making it the divider, the thing that's dividing the numerator, the denominator of this equation, will get smaller and smaller and smaller, and so VAV will actually grow a bit. So, how do we do this in practice? What does it mean to shrink an interval? Well, in calculus, we call this a limit. So V, and I'm going to call this the instantaneous velocity, V, is equal to the limit that we take as delta t goes to 0 of the equation r wherever delta r over delta t. And what we end up with when we take this limit is we end up with a derivative, dr dt. And so, if you're not familiar with limits, I would look into that a little bit. A limit just means exactly what I've drawn here graphically, which is that I take my time interval, which are these little marks here, they're also the spatial intervals, and I shrink them down to the shortest possible limit as delta t goes to 0, gets really, really short. My vector delta r becomes a differential vector, a very small piece of a vector, and it's just really it's the deltas of my change in position, and that's becoming now a differential, which is delta r. And delta r divided by this limiting value of delta t going towards 0 gives me a value for the instantaneous velocity that looks a little something like this. Now, the velocity, average velocity that I got for the vector that pointed from b to c divided by this time interval probably looks a little something like this. This is v average defined as delta r from c to b over delta t, and I'm still going to label this c to b. This is v. This is the instantaneous value. The other interesting mathematical point about this is that this velocity vector is tangent to this point at b. And that is how these velocities in this limit are defined. So this is a vector quantity, and as such it has components. And so we can write down the components of our velocity vector v, and they are really just the derivatives of r with respect to t. So we can write down v is equal to d by dt of r. I've just brought the r down, so it's a differential. And I can now put that into the bracket dr sub x dt, dr sub y dt, and dr sub z dt. These are not vector quantities. Okay? So this is how we define the velocity, the instantaneous velocity for our vector r that's changing in time as the limit as delta t goes to 0. Okay, so that's how we define velocity.